A child in a boat throws a 6.4 kilogram package out horizontally with a speed of 10 meters per second. Calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the child is 26 kilograms and the boat is 45 kilograms. Ignore air resistance. Oh, okay. That should not be too bad. So in other words, you've got the child,
Yeah.
you've got the boat, and you've got the rock, right?
Mm-hmm.
And what happens is that the child is, so the package is 6.4 kilos. The child is 26 kilos. And the boat is 45 kilos. Now, you know that this is, do you know what law we'd be applying to this question 6? Question 4. Do you know what law would be applying?
Conservation of momentum.
Yeah, conservation of momentum, because although it's not a collision, it's a explosion, right? You're separating the object, right?
Yeah, because like that's a part like I don't understand, because when I check the answer of this question, it says like you see this as a like interaction between two objects, like collision. So I'm a bit confused, like why this was like why can't you apply conservation of momentum on this situation?
Right. So you're probably used to the fact that you've got object A crashing into object B, and then, you know, depending on what information they give you, do the calculations based on that, right? That's probably what you're used to, right?
Yeah.
Are you familiar with the example where you've got an object A, and then it then becomes, you know, object A1 and object A2 and object A3? Like it blows up into 3 pieces. Say.
No, never did done.
Yeah, so as I said, we never really had the chance to do collisions. I mean, you know, we were focusing on energy, right? And I just told you the rule. But yeah, conservation of momentum applies to collisions and explosions.
Okay.
So in other words, you could have, you know, objects, you know, interacting with each other like a collision, probably most questions you get. But you can definitely also treat it as an explosion, which is one object separating into multiple objects. That is not a collision. It's called an explosion, but conservation of momentum applies to that as well.
Okay, cool.
So in other words, though, here, can you see that basically at the start, everything's together, all 3 objects are together.
Mm-hmm.
And afterwards, you know, one's left. One's being thrown away.
Okay.
So that basically means that it's an explosion.
Mm-hmm.
So therefore, we just need to work out the mass, like at the start, what's the mass? So initially, it's probably quite clear. The momentum is 0. No one is moving, right? Doesn't matter what the mass is.
Mm-hmm.
But afterwards, because of conservation of momentum, the momentum sum afterwards still needs to equal 0, right?
Yep.
But that is made up of the momentum of, I guess, the child plus the boat, plus the momentum of the, what do they call it, package. Does that make sense?
Yeah.
Now the momentum of the package is equal to m times v, and we know both of those things. It's 6.4 times 10. I haven't written it here, but I remember the v is 10, right?
Yeah.
And in other words, we can work out the momentum is 64. And I'll just leave off the units for now.
Mm-hmm.
But that means if you're throwing it and giving it a momentum of 64 that way, and they need to add to 0, that means the momentum of the child plus boat is negative 64.
Mm-hmm.
And the mass of the child plus boat is 26 plus 45, which would then be 71.
Mm-hmm.
So therefore, the velocity of the child plus boat would be the momentum divided by the mass, which would be 64 over 71. And that would be, you know, we could work it out as a decimal, but that would be the answer.
Oh, okay, cool. Yeah,
It would be 0.9 meters per second the other way.
Yeah. Because like the part of this question that I don't understanding so why you can apply conservation of like the momentum on that. So
Yep.
the
Yep.
other people then finds it.
Yep. And as we said earlier, it's because, you know, the rule of conservation of momentum is not just to collisions, it applies to collisions and explosions. So you're correct to kind of think that it's not a collision, because it's not. But it's just a different type of interaction called an explosion, where, you know, conservation of momentum also applies, and you can definitely be tested on that. Even if it's rarer, you can be tested on that.
Yeah, because like in the class, like definition of the conservation of momentum law, when we talk about that, like she only said collision.
The word explosion never ever came up.
Yeah, she never mentioned that. So like that's why I'm a bit confused. Because
Okay. They should mention it. I would stress the collision more than the explosion, because, you know, nine questions out of 10 will be a collision question, and, you know, maybe 10% of a question will be an explosion question, but you can definitely get tested on it.
Okay. Cool. Okay. Yeah.
Any other questions you want us to run through? Question 9. During a Chicago storm, winds can whip horizontally at speeds of 100 kilometers per hour. If the air strikes a person at the rate of 40 kilograms per square meter and is brought to rest, estimate the force of the wind on the person. Assume the person is 1.5 meters high and 0.5 meters wide. Compare to the typical maximum force of friction between the person and the ground if the person has a mass of 70. All right, so that's the second sort of question. All right, so you probably won't get a question as complicated as this in your test. Having said that, there's no real reason why you can't actually do the question.
Yeah.
Like the concepts are there, and it's just I guess usually most schools won't give you questions like this, but there's no reason why you can't do it. So let me show you how you would do it. All right, you know you've got wind. So imagine this represents wind, and it moves at 100 kilometers per hour. And that it strikes the person at a rate of 40 kilogram per second per square meter. So it strikes at 40 kilogram per second per square meter. So basically it's saying that for a certain area, you know, you get hit with this much mass of air per second, right? Now you have a person, and it's brought to rest. So it was moving 100 kilometers per hour, and then it's brought to rest. Now, you've got a person who is 1.5 meters high, as well as 0.5 meters wide. And that's our assumption. So therefore, what's our area of the person? Think of them as a rectangle.
Okay, so you like 2 times 2. No, 2 times. Oh wait. It's 0.5 times 1.5.
So it's 0.75 square meters, right?
Yeah.
Now that's the area of the person, but you are told that you are striking it at 40 kilograms per second per square meter, right?
Mm-hmm.
So because you've got 0.75 square meters, therefore the mass per second is going to be 40 times 0.75, which is 30 kilograms per second. For the person, they're being struck with 30 kilograms of air per second.
Okay.
Now, they want you to estimate the force of wind on the person. So here's where here's where it's more directly to the physics, right? This is just sort of in general, making the question more complicated. But more importantly, what you need to understand is, you know that there is this amount of air coming in mass, mass per second at this speed, right? Which we need to calculate, change into meters per second. And this wind will then hit the person and go to rest, right?
Yep.
And so we can estimate, well, not so much estimate, we can calculate the change in momentum, right? For the wind, change in momentum for the wind. So for the wind, in 1 second, you've got 30 kilograms, right? Times 250 over 9. So that's how much momentum it started with, because you've got 30 kilograms moving at this speed, right?
Yes.
But it then goes to rest. You're told to assume it goes to rest. Which means the change in momentum can be calculated, and it will be this. That's your change in momentum. Now, what is change in momentum also known as?
Impulse.
Correct.
Oh, yeah.
And what's impulse? What's another formula for impulse? With relating it to force. Relating to force.
Well, force divided by mass.
It's equal to force times time.
Okay. Yeah.
We're trying to find force, but we know the time is 1 second because we said it so. Because t equals 1, therefore force must equal that many newtons. And that's basically the first part of the question done.
Okay. Okay, yeah.
The second part of the question is just to compare against friction. So this is really just more of a calculate friction thing. So the normal force must equal the weight force in this situation, which equals mg, which is equal to 70 times 9.8. Which is equal to 686 newtons. And so if the friction force is mu n, which mu is equal to 1 in this question, then it's 686 newtons. So we would say that this is not good. We would say that the force of the wind is greater than the friction. Which is around 833. So what that means is that if you are in this situation, you won't be able to stand very easily. Like you'll be blown backwards. So yeah, if you're in 100 kilometers per hour wind and it's, this dance, then yeah, you're going to be blown backwards. Under these situations, you're going to be blown backwards. Yeah. Okay. Like if you literally stand on the ground, you'll be blown backwards.
Okay, yeah.
Does that make sense?
Yep.
Good. So I will, as I said, you probably won't get a question quite this complicated. I mean, the fact that you want to link change in momentum to force is definitely consistent, but your test is likely to make it much easier, like much fewer steps to calculate what the impulse is. Right. Instead of giving you the area and this and all that, they might just go, this amount of wind hit a person and stopped, something like that. You recognize we have to do like 1, 2, sort of 3 steps to get to impulse. They'll probably, and we have to do the conversion here as well, they probably would have just, simplified that down to 1 or 2 steps.
Yeah.
Yeah.